And Dixon sold a version which was really quite a nice calculator for its time. And Tony's now going to tell us about the 8-segment displays in these.
Yeah.
Thank you, Tony.
That's nothing to do with it. Just not put a picture up when I talk.
No, I'm looking at the feline of
cat,
this.
yeah.
Unfortunately, the feline is now beyond repair.
Let me know where cat it comes from.
But the computer's not beyond repair, but I'm not talking about that unless you want me to. Anyway, some weeks ago last Thursday, I was walking around the hall when I met a man who was selling quite a lot. There was sorts of odds and ends of no interest to me at all. And the 4-function calculator that I bought. Right, and 4-function calculator not generally that interesting, right? Mm-hmm. And it is the obvious 4 functions. You know, add, subtract, multiply, divide. And it's not programmable or anything like that. No, it's got one memory. And make matters worse, it was badged Prinztronic, which was a brand used by the Dixon's high-speed camera and audio shops in Britain. So it's hardly going to be the best quality. And yet I bought this thing. So why did I buy it? Well, I thought, there's something unusual about this machine. Something unusual about that. I thought, am I right about this? So I got it home. And I did what you always do when you get a calculator home. I took out 2 screws on the back. Expect to be very badly made, of course. And took off the cover. And that's what's inside it. This is a battery. This was originally a battery pack and a circuit board. And my first aim was, is a battery pack, is it leaking? If so, can I stop any more damage? I want to see how badly made it was. I want to see if I was right about the odd feature. Well, you can unclip the battery. And there's a little cable with a plug you unplug. Like that. That's the battery. Take out 2 more screws. And this is the power converter. The earth wire to unplug, earth all the metal parts of the case for anti-static precautions. And there's a little connector there you unplug. So you have a power converter. And then display. And logic. Oh, here you come. That's the logic board out. And what's left in there is the keyboard. I'm not going to take the keyboard out, it is just 2 more screws at the bottom. But all the screws so far have been machine screws into metal bushes. Whereas that one are 2 self-tapping screws into the case, and I don't want to wear the case out, the plastic. Now, so that, and this is the first real slide of the talk. That shows the thing dismantled. Top case, keyboard, logic board, display, power converter, the main modules. Okay, so what? I'd noticed in the part there was a bit of corrosion on that plug that goes to the battery. So I thought the battery probably is leaking internally, but it hadn't spread to anything else, so it wasn't a complete wreck. I thought, well, the odd feature, surprisingly, is the display. Which is in, now, if you look at eBay, you will find people selling calculators with green LED displays. Green LED displays do exist, but they were never used in handheld calculators to my knowledge. But of course this is clearly a green display from the window, you can see the light. So it's clearly, and in fact it's what's called a vacuum fluorescent display, which could be more accurately termed a light-emitting triode, modern light-emitting diode. It works like an old valve triode. At the front of the display tube, there's a a thin wire filament, which is operated just below red heat, so you don't actually see it. It emits electrons. There's then a control grid, which is normally run as a positive volt, acts as an accelerator. It pulls the electrons through onto the fluorescent material coated anodes. Okay? Now, and they glow. And you can use the grid to completely cut off an entire digit if you want to blank an entire digit. So you could multiplex by turning one after the other and scan the display as a multiplex scheme, which is what is done normally. Now, you all know, I hope, the 7-segment display patterns. If you don't, you're in the wrong club. But that is a close-up of the right-hand half of the display. And that's clearly not 7 segments. I mean, is that L-shaped segment? There's a curve on there. And in fact, if you have a look, there's 1, 2, 3, 4, 5, 6, 7, 8 segments. You never count decimal points. You don't count the 7 segment and count it here. So there are actually 8 segments in the display. That thin wire there, you can just about see that line, that is the filament. It emits the electrons for the tube to work. And this sort of honeycomb structure, that's the grid. And the anodes are behind that. Right. Now, given that, I think it's fairly obvious that you are unusually shaped digits you get from it. That is what 1 up to 8 looks like. Being only 8 digits, I can't show them all at once, but anyway, there's... Some of them are more readable, some of them are less readable in my opinion. I think it's more what you're used to be honest. I mean...
Cursive.
Yes, and then there's the remaining ones. The 0 is a little 0. I'm told, incidentally, this is not in my talk notes, that Casio did a few machines with 7-segment displays where the O was the bottom square of the 7 segments, rather than what you expect. Anyway, so the display module itself is just the tubes, and it is theatre multiplexed. There are 9 tubes on that display, 8 digits and the enunciators, which you could see in that last picture, and they're done in groups of 3. The leftmost 3, the middle 3, the rightmost 3, the enunciator on the far right, and then, so they're all driven together, and then the grids are you set 1 tube in that each group of 3. So it'll say do those 3 digits, digits 2, 5 and 8, or digits 1, 4 and 7, or the enunciator digit 3 and digit 6 together, and then move to the next one. One oddity though is the filament wiring. Now, if you have a look, the filament voltage is supplied here, VH, and it returns the negative VD line, and this half of the chain has got 5 tubes in it, and this half, so that's 5, and then this half has got, that's right, this half's got 5 in it, that one, and then the other half go from here, that one, that one, that one, and that one, but you've got 4. How does it balance it out? Well, of course, there's a trick. We go back to there. These tubes have got 1 filament wire in them. This one has a pair of filaments. It's got 2 filament wires in it. So presumably the enunciator tube took twice the voltage of the filament of all the other tubes. And that is how it balanced it out, because the enunciators are in the 4-section chain. I'm showing my age now. When I started electronics, we had radios with DL96 output valves and DF96 IF valves and things, and the output valve had 2 filaments and took twice the voltage if you ran it in series to get a bit more power, but anyway. Now, so that's the reality, is this display, because it's such an unusual pattern. But the second thing is, it was a Dixon's machine effectively. Admittedly it was, as Alex said, a rebadged Sharp, apart from the colour of the case. And how good was the build quality? Well, let's look at the keyboard, which is always a good thing to look at. This is the front of the keyboard. You can see it's got 20 keys, 10 digits, and the others. You've got change sign, decimal point, 4 operations, clear, look at extra memory recall and clear, and memory plus. The memory is actually accumulated. There's no stored memory. You start with a clear memory, you just keep on storing into it. And if you press that once, it recalls it. You press it twice, it clears it. In quite a succession, that is. You can record many times like we can't. No source said that plus equals and minus equals. It's pseudo RPN for addition and subtraction. You add, but if you want to do 3 minus 2, you do 3 plus equals, 2 minus equals. The other trick for the unwary is that multiplication division automatically set a constant. To clear that constant, you hit the minus equals after pressing the plus equals, and that clears the constant mode. That's actually documented on the label at the back of the machine, so I found it. So, I decided to dismantle a keyboard. I dismantled it on my workbench, took it out, and it comes apart. These are the guides to put the logic board in, to guide it into the socket on the keyboard. This is the key frame, this is the keyboard PCB. Okay, it comes apart fairly easily, a handful of screws. Now that is the circuit board on the keyboard, this circuit board here, turned over. These are these are reed switches, driven by magnets. It's a very reliable contact because you can't get air to it. They're sealed in inert gas. So they're very reliable, they don't oxidize, you don't get keyboard trouble. They're operated magnetically. This is the back of the keyboard frame, this thing, so you can see it there. When you press a key, it moves the key plunger, and that moves a magnet down, these are the magnets, which operate the switches. So it's hardly a poor quality build.
It must have been expensive.
I think it was. I think back then all calculators were expensive, to be honest. It's early 70s.
It would be expensive.
It would be expensive. I mean, you know, HP. But what my comment is, I think this is as well made as a Hewlett Packard at the time.
Oh.
If not possibly slightly better, it's
Do
just
you
whole
think it
thing.
would have been made by Sharp?
It's made by Sharp. Definitely. I mean, the main circuit board says Sharp on it. Oh, it is. It's known to be. I mean, you know.
So this is an early generation calculator
Yes.
by Sharp?
Yes. There was called. It was an EL-811, I think it was. Sharp used the term EL or LC, ELSI, in the LC made through the LCD era. And that stood for extra large scale integration. I'm serious about this. It's because anyway, that's an aside. If we go down, 20 keys, 12 wires back to the logic board on the connector, that suggested instantly to me a 10 by 2 matrix. Think about it. 10 one way and two column lines. And in fact, that's what it is. You've got 10 key lines, 0 to 9, and a common 0 and a common 1, and the digits are all in one, and the functions are all in the other. And there's no obvious way to number them, other than say I'll number them by what the digits are, as they're all in one column. That makes some sense. It makes more sense actually later on. Now, I'm going to say a little bit about logic circuit board. This is the main calculator logic. There are 6 chips. These 2 ones here I can say nothing about. Those are the calculator logic. I know nothing about them. I've got no data sheets. But that's the calculator chipset. I usually say Sharp on it, on the circuit board there. These 3 up here are the display drivers. That's where the display plugs in. And this one on here is related to the keyboard. Those 3 discrete transistors, by the way, are the drives to the grids to select the individual digit in each bank of 3. And as we see now, the display drive, this is the display socket, there is one display driver chip for each, for the leftmost 3 tubes, one for the middle 3 tubes, one for the rightmost 3 tubes. That's how it's wired. It really, these chips are effectively 9-bit shift registers. 9-bit, yes, the 8 segments and the decimal point. It loads a 27 bits in, cycling through them. That's why it's not wired, it's nothing more digits. Sets it up and then turns on the appropriate 3 tubes. And that is the circuit for the display driver. And this, the display driver uses a 2-phase clock. This is the clock waveforms. It's about 100 kilohertz cycle time on the display driver. Some idea. And that is my favourite HP handheld, of course. I think he's got one, haven't they? But They're beautiful, those things. So that's that. And here we see the 3 transistors that drive the grids and the keyboard interface. This is where the keyboard plugs in, the 10 key lines and the 2 common lines. There's that chip in the bottom corner of the circuit board. And then lines 1, 2, 4 and 8, for those digit keys, what a surprise, are clamped and then fed onto the processor. The other lines do not go to the processor, only the 1, 2, 4 and 8 lines end up going to the processor, the calculator chipset, 2 big chips. This chip somehow encodes the other lines into some pattern on those. Now look at that chip very carefully. Something very unusual about it. Has a negative supply, but no positive supply connection. So how can it possibly work? Well, the answer is, the only reason for that is, when you make a chip, you're putting down regions of N-type and P-type semiconductors to make components. You end up with extra diodes you didn't really want, simply by having those regions next to each other. And the way to avoid this is to reverse bias them all by having something going to the hard negative line. So they make no difference to the circuit. That's the only reason for that. So what's inside that chip? The amazing answer is that is what is inside it. It's just a whole lot of diodes. So for example, if you press the 6 key, it turns on the 2 and the 4. Exactly. It's a binary input to both. Remember I said it was the 1, 2, 4 and 8 lines. You press 9, sends 1 and 8. There is one exception to that. Pressing 0 would be a waste of time. It would send nothing. 0 sends 2 and 8, sends us a 10. This of course reminded me of telephone dialing for some rather weird reason, but... Now, I'm going to say nothing about the power converter, because it's not my interest. If you want to know about it, ask me. I can say how to rebuild one, but there's nothing clever about it.
So the diodes is one of those chips you did.
That little chip in the corner is just those diodes. That's all that's in it. No transistors, nothing else. Just those few diodes. It's a diode array. Nothing more.
Was that something they used to use in those days?
Oh yes.
Oh, yeah.
Oh yes.
I'm not a hardware guy, so.
No, they did. You could get diode arrays of standard patterns, and presumably this was a custom-made one for that purpose. But I'm going to end my talk by talking about the battery pack. That's the thing that's most likely to have failed. Now, some people here have rebuilt HP battery packs, had to crack the casings open. So, what was this one like? Well, there was one metal rivet that was in that hole. So I squeezed it, you couldn't really drill it out because it was just spinning the hole. And it's quite badly recessed. So also notice that hole is slightly hexagonal. Come back later. So I squeezed that rivet with pliers carefully and got it out. And then, you're going to love this, it opens as a clamshell. Now admittedly it's just a thin web of plastic down there, but nonetheless it's very easy to open. And you see the cells have leaked a bit, but the leaks hasn't got too far. So I took the bits out, and I dropped them in citric acid.
What kind of cells?
They're AA NiCads. And 6 of them. The leakage is potassium hydroxide mostly. It picks up CO2 from the atmosphere, you get potassium carbonate. So you drop it in citric acid, it fizzes a bit and dissolves. And so I get it all cleaned up and took it apart. And I found the biggest problem. The corrosion had seeped along the wires inside the insulation. That's why I got corrosion on the plug that went in. That's the little socket on the battery pack. So that's why I got corrosion on the plug pins. It actually got there. Now the problem was I wanted to reuse that socket because it's a custom moulded socket. The 2 pins are different sizes. It's polarised. And I had to cut the wire right back to the socket in order to make a connection. But I did manage to do it in the end. And that's me. What I'd done there, this is the socket from the battery pack. I'd soldered some extra wires onto it. The original battery was 6 NiCad cells, nickel cadmium cells. That's 7.2 volts or thereabouts. Here's 7.5 volts from primary cells. And that will run the machine, and you power it up, and that's the power point is about 24, 25 volts. That's offload minus 26 volts. So that's me just testing the power converter, make sure it actually works, and it did. Now, I actually put the machine back together and had the logic running like that, but it's clearly impractical to run the machine like that for any length of time. I mean, you want to have battery back. So I thought, well, hang on. We have the mains charger. It does actually output enough power to run the machine. Because if you can charge the battery it's running it, the battery has two functions. It stores energy, and the output of that charger is pulsed at mains frequency. It's a pulsed signal. So you want to have something to store, a capacitor or something to store that. And it also limits the voltage. So I thought, right, let's tag a couple of capacitors and a couple of Zener diode, I have to put 2 in series at the right voltage, on the output of the power supply. What happens? It works very well. And so I thought, this is a good idea. And then, of course, these two terminals it's connected to end up going down this flexi cable to the calculator, and they go to the 2 pins of the battery. So I thought, well, the obvious place to put those components is in the battery pack. So I mounted one of the strip board, put it in the battery pack, and that's what's actually in there now. And I then put it back together, and I mentioned that hole by the mirror also slightly hexagonal. It's a 5mm hexagon, and then 2.5 nut fits perfectly, so it's back there with a nut and a bolt. It is much easier to rebuild than any HP battery pack I've ever worked on. And that was the end result. Now, my question is, see that number, 3.1415929, what is it? And how did I generate it? I'm wondering how I should do the obvious. And slot the logic board back in. There you go. Thank you. That's it.
355 over 113.
It is.
Indeed.
It is indeed. It's a very common approximation to pi. 355 divided by 113. Put the display in, and we'll couple up the power converter. How did you know that, Frank?
Well, I had to check that the number came out correct. But I know it's very close.
Yes.
It's much closer than it should be, given only 6 digits. It's a good approximation.
It's because I believe, and this is much more Jeremy's field than mine, the continued fraction approximation to pi has a very large number and denominator at that point.
1 over 292.
That's it.
Is it not easier just to
Yeah, that's
remember the
right.
numbers from the front?
Well,
This is 1,
well, 355 divided by 113 is a classic.
Very easy to remember, that's the point.
It's easy to remember.
It's one I use a lot because, to be fair, the battery. Now, will it power up? If I put the cover on, might see it won't, but we'll find out why not in a minute.
Oh, I see smoke.
Yes, it does. Amazingly, it still works. So I'll put the cover on. Put the cover, there we are. And so that is one of the very few Dixon's branded products that's actually worth buying.
The main clue
Rebranded from Sharp.
to quality on that one, poorer quality than HP, is flux on it still. You don't see flux on HP.
No, on the other hand, HP assembles self-fabricated into plastic and machines used into metal here. The battery pack's easy to rebuild.
Oh yeah, absolutely. Yeah.
All the connectors are gold-plated, to depend on the
Yeah.
quality machine. The keyboard read switches. It's actually a well-made machine,
Nice.
to be
It's a very
fair.
well made machine. What year would you say this was made?
About 72, 73?
Okay, so
I wonder
very
if
early.
actually, I wonder if they date codes on the chips.
I mean,
I've got an idea.
what is the actual trigger voltage for the
That I think is 1972 on that chip. 7203. That gives an idea of the date.
Okay, so that would be the date.
Yeah.
then. And you know the little valve which
Yes.
are the display units.
What's the voltage?
Yeah.
About 30 volts. 25,
About
30 volts. It's
And
quite
that
low.
voltage was created by
About that power converter.
the power converter.
Yeah.
Okay.
I mean, if you, I'll say something about that. I can.
No.
So what are these chips then?
Which chips?
The 2 big ones.
2 big ones. They are a Rockwell chipset I know absolutely nothing about, I'm afraid.
Invested in no time.
According to Multiply, they are 105735A sharp.
Oh, those.
They were made by Rockwell, I think you'll find. I mean, I can. If you want to know what they are, hang on, maybe.
It's a shame I couldn't have found it, because this would have actually segued quite nicely into your talk, because I've got an old Casio Biolator. Does anybody?
I remember that, the biorhythm one.
Yeah.
I remember
I've
that.
got one in perfect. Well, I bought it when I was young, when I was interested in biorhythms. Whether it still works, I don't know, but I'm not sure where it is. But I know I've got one at home.
Interesting.
I'll bring it in next time.
on my sign.
Well, no, the Biolator is unusual.
Those are the calculator chips, by the way. I don't know about them. That is the pair chip. 10573 and 10571 are the two chips in this board. I mean, that's the display scan, display data. That brings the IOs. You've got this display scan, display data, and the keyboard interface. So that's probably the calculating engine. And the display clocks are brought off that, but I know nothing about what goes on the lines between them. It's some sort of sequence. That's presumed. If I had to guess, I'd say that was equivalent to the control and time. That was going to do arithmetic and registers. That's a guess based on what they're wired to. But it doesn't say very much. And I mean, everything is. That's the power converter. It generates about minus 24 volts effective around there for the logic and the displays, and a little voltage there for the filaments in the display. But it's nothing. It's the voltage I showed you. I was measuring about minus 26 volts on the meter. That's the voltage you put on the display. That's the order anyway. Now, if anybody wants it, I have my talk notes, the slides, right, the full circuit diagram, all the pages, that's all these pages, and a total of, I think, about 50 odd pictures of the machine, including the ones in the slides, not another 50 pictures, but you get more pictures of the battery pack and more bits of it in dismantled and things. If anybody wants that, it's about a 300 megabyte zip file, but just bring a memory stick and ask me and I'll put it on it for you. And
fascinating.
If you want, Mark, if you want it for the website, you can do that.
Yep.
Any more questions?
A very good talk.
I missed on the rebuilding the battery pack. Why did you not rebuild it?
Why they put cells in it? Yeah. I could have done, except I'm not likely to use this machine very much. Let's be fair. It's going to be used at the demonstration, so having to plug it into the mains is not a major disadvantage. And to go out and buy 6 NiCad cells, not the easy things to obtain now, but you can get them.
Yeah, 20 quid's worth.
20 quid of NiCad cells, as Andrew said. And they will probably decay long before I've done them very much. I'll take this home tonight, I'll pop it in my drawer, and I probably won't bring it out for another year, which for the NiCads to be ruined. So I might as well put that little clutch circuit in, which works which lets me run into the mains adapter, and use bits from the junk box and B bits that will last a long time.
I just missed whether the internal connectors had corroded away so much you couldn't reuse.
But I wouldn't really want to. I mean, the battery pack internals. It was just a cell. I had to reuse the connector anyway for the because I had to plug into that cable from the pack. I had to plug into the that cable. I mean, this is the original battery pack. It's exactly what it appears. The socket and 6 cells, and so I had to reuse that socket. The cells were joined by having a spot welded tape, but I could have soldered them. There's enough space to do that. So I could rebuild the battery pack. I mean, you could rebuild them if you wanted to. In fact, what I found very odd is, in one of the Sharp user manuals I found for this machine, the Sharp manuals, they actually tell us an end user to remove the back cover and swap the battery packs out.
What, you mean the cells or the pack?
No, the pack. I can take out the 2 screws, take the cover off, unclip the pack, pull the plug out, put it into the new pack and put it in. He almost suggested keeping a spare one charged and sort of changing. You couldn't change mid-calculation because if you've got any low battery problems, you could change the battery.
So this was sold as an 8 Sharp, was it, as well?
Yes, it was sold.
Just
I'm
rebranded.
told it's a different colour.
Right, okay.
The case molding, but I'm not very bothered about it. I'm not one of these collectors who collects by colour. I collect by internals.
By function.
Yeah, by design. Not saying by function. I mean, yes, 4 functions are boring. Let's be fair. I love a good programmable, but equally, when it's got some interesting, unusual display,
Very unusual.
it's worth adding to the collection. And it didn't cost me that. I think I paid £20 for it, when we asked.
How similar is the display technology to the Casio Biolator of a...
But the display tubes were made by a company called Itron, who made them for all sorts of things. And basically, there were some machines that included them have individual tubes, one per digit. And you could also get an array where you had the anode layer with the anodes linked together correspondingly, then the set of grids, then long filaments across the whole thing. In a flat glass package evacuated, which was in one displayed for all the digits on your machine. And that was using, by Casio, if you think of the famous FX39, all that series of calculators, the green Casios of the 1970s and 1980s, which I think most people will remember, that's what they had in them. The display technology, how it works, is the same.
Same principle.
I don't know if Itron ever, I don't say Casio used Itron display, but the technology. And in fact, even into the sort of 1990s, you would find home video recorders, VHS video recorders, with those sort of displays on them.
Yes.
Because of course, you're not stuck with green. You could have fluorescent colour, any colour you like. So on a video recorder, your recording indicator could be red, for example, by just having a red fluorescent material on that anode.
Car radios.
Car radios. A lot of them now are backlit LCD, I may add. What is?
That's the Sharp.
That's the Sharp one.
So it's silver.
Yeah. That's the Sharp one. But it's absolutely the same machine inside.
It's even got the same sticker
Yes.
at the top of the keyboard, doesn't it?
But they're double sub-molded keys, not stickers.
No, just above the keys. Isn't there a sticker on it?
There is, which reads,
It's the same one.
K on constant cal,
Yeah.
and then an arrow to the minus equals reset key of constant calculation. Yeah, that's it.
It's the same
Yeah.
stick.
Same machine, yeah.
It is. The keys are a different colour. They're white with black mark. It is different colour. They're the opposite way around, the key markings. Do you see what I mean? But they're negative images. But I mean, it is the same machine, apart from the colours of plastic they used.
And you bought this for how much?
20.
So that was twice, and that kept you busy for how long?
A couple of weeks. Cheap entertainment.
£20 for the time it kept you busy. Would you rate that as the all-time probably best value for money?
Oh no.
I have spent more money, but given me a lot more amusement. You say, if you're wondering about the introduction to I talk about some weeks ago last Thursday. First of all, Thursday in Bromley is the day of the antique market, which is why I got this. And unfortunately, Philip Belwood is not here, so he can't tell you what it's a parody of.
Fascinating.